One of the key properties of this material is their flow properties or ability to modify the viscosity. For example, one hydrocolloid can make a solution that you can easily pour, where the other can make it a lot thicker and more viscous. Other type of hydrocolloid, they can be gels at room temperature, but once you heat them, they're melted and they be poured as a solution. And this is really the basis of how they use in various products. And how do they do that? These are basically sugar units, as you heard from the previous speaker. Fruit juices and others, they're all sugar units, but these are monomeric sugar units are linked in a certain way. As an example, cellulose, cotton, it has a linkage of beta-1,4 glucose, and this gives us a strong fiber and water-insoluble material. If you have the same sugar unit, but change the linkage from beta to alpha, you basically have amylose, which is part of the starch, and this gives us a weak powder and water-soluble material that completely dissolve in water. Some of you had the chance to have a look, but in case you haven't, here at Chester we are well equipped with excellent facilities, really to allow us not to look at the food formulation, but look at all aspects of food as microbiology and others. And this is example of some of the lab downstairs. One of the instruments you've seen in the previous slide is basically allow us to measure the solution property of rheology, as you heard from Neil. And here we measure the viscosity as a function of shear rate or moving the sample. And what you will see that these hydrocolloid, depending on their structure and the way they interact with each other, they can form various conformation, and this type of a conformation will really determine the type of thickening or ability to viscify a solution. For example, xanthan, which is a bacterial polysaccharide, at 1% gives the highest viscosity, but once it's shaken or sheared, it will lose the viscosity very quickly. And this is one of the main reasons why it is used as a thickener or stabilizer in salad dressing. Other hydrocolloid like pectin, hyaluron, carboxymethylcellulose, they form viscous solution at different concentration, and they have a certain viscosity at rest. But once you start to shake them or apply some force, the viscosity will decrease. And compare this to gum arabic, at 30% it makes the lowest viscosity, and its viscosity does not change drastically when it is shaken or sheared. And this is how these materials are used in various food products. The lower viscosity is used obviously as a good example of a dietary fiber, because you can take a lot of this material and still you'll be able to drink it as a drink, where xanthan at 1% concentration, increase it a little bit, you will need a spoon. So, and this is the ability or the conformation they can make in solution as shown here. And this is the example of xanthan. Great deal of uses in the food industry, but also some technical uses in the oil drilling. And here, for example, one of the formulation we've been involved in, working on this rosette. And xanthan is part of the formulation. And what it actually does ensures that this rosette will stay stable. And the action xanthan provided in this particular example is really providing this viscosity. This is the type of work that we do here. Xanthan is used in the industry, and when it's used in the industry, and I should have mentioned, these natural materials are really not standard. So when you say xanthan or you say carboxymethylcellulose, these could be very different depending on various factors. And my student Yasser will talk to you about his work on gum arabic and how he went to look at various plantation and take this material from different trees to identify the quality associated as a function of location, time of picking, age of the tree, and so on. Xanthan is also another example because it's a bacterial polysaccharide, and depending on how it is treated by the manufacturer, it could have some variation. But subsequently, when it's used in the industry, it is subjected to various conditions such as heating, sterilization, such as autoclaving, also higher pressure homogenization. And this is the paper we published on the latest on xanthan. There's two views in the literature, and this is a purely scientific. One will say xanthan is actually double helical form, and the other publication you will see this, it's not exactly a double helical form, but more of a random coil that it is built in a way to give you this viscosity. And what we demonstrated using atomic force microscope in collaboration with the Norwich group, that the two areas or the two regions are actually present. And this came directly from the measurements of the height. When we measured the height, you can see that it's clearly two polymers or two chains, and also the single chain could be identified. And this is the schematic diagram that we propose will result in this various treatment. Another example I will use is pectin. Pectin is extracted from the as a cell wall polysaccharide and industrially produced from the waste product of the apple romance and the fruit, the orange juice. And what you see, pectin here is really building all of these cell wall and providing what we call the integrity of the matrix, because it has ability to hydrate. So it is in between the cellulose and the hemicellulose and pectin interpreting these chains. This is the type of structure that's been proposed for pectin, and it is basically a long chain of galacturonic acid with some side chains with the neutral sugars. But the interesting bit about this, that these galacturonic acid, they could be methylated, and depending on how much methylation, we call low methoxypectin if it has less than 50%, or high methoxypectin. And the two are used in various applications. For example, pectin has ability in the presence of metal ions such as calcium to make what we call, according to the egg box model, an excellent gelling material by bringing two chains to make a nice gel. But pectin also able to form hydrogen bonding if it is acidified. Pectin is also capable of hydrophobic interaction to form these type of gels. And this is where you add the co-solute like sugars. In the making of the jam, the sugar will go for the water, and this will leave pectin really to come together, and this is the basis of making the jam. So these are part of the interaction pectin capable of, and they have been utilized greatly in the industry to fine-tune the structure and develop a formulation or product that could have the same characteristic irrespective of the material. However, due to the natural built-in variation, companies or producers of product have to ensure that the material or the raw material they are using, it will perform exactly as they would expected day in, day out. And this is where they come to us to work on the material and advise them on what type of pectin or batch that will be suitable for their product to be used in one of these, as you see, the bakery, in pharmaceutical, in the beverage industry, in the confectionery, and so on. And this is one of the work that we've done on looking at various commercial low-methoxypectin. A company patented a product which is basically a double emulsion encapsulating a flavor, and then this flavor then encapsulated with low-methoxypectin. So when it's dissolved in the formulation, it could be released gradually rather than you have a sudden hit of the flavor and then it disappears. And this is the type of work that we reported here. The other example I have is gum arabic, which you will hear, as I said, from Yasser. This is an example of a tree exudate, basically from the Saharan belt in Africa, Sudan, Chad, and these countries. And here the tree is manually wounded by removing some of the bark. And the process of gummosis, or exudating the gum, is really part of the defense mechanism of the tree to protect itself and keep or seal the wound to keep the moisture. So it exudates this gum, and this gum later on used in various formulation, confectionery, a binder, a film former. It has excellent film forming ability, and the more recent legislation actually produced this material with health benefit, and now it's been used as a possible dietary fiber, and it is being regulated as an ingredient. So it's no longer an additive, it's also an ingredient. One of the application or the heavily used application of gum arabic is the ability to emulsify oil in water. And I have been specifically asked to say something about emulsion. Basically, emulsion, when you have water and oil, they will not mix, the oil will be on the top. But what happens when you start to mix it or use high energy? This is the type of droplet that you will produce in the system as a function of the energy you apply. If you use a spoon, you'll produce certain droplet size. If you use a homogenizer, you'll produce different, and this is what you will see, the droplet size distribution from nano to micro emulsion. And this is all making the emulsion is one side, but there are a number of things that could go wrong with this emulsion, and this is the type of work also that we study. And coming here to university, we have to show you an equation, and this is all governed by this equation, but I will not deal with it. I'll just show you the type of thing that could go wrong. And here you could have two droplets aggregating, and this will lead to making a larger droplet. A larger droplet will basically mean taking all the color or the flavor to the top, and this is what you see, or what we call ringing. The other one is the coalescence. Two droplets come together to produce a larger droplet. And again, this is a recipe for a failed emulsion. The other one is Oswald ripening, and the best way to describe it, the big become bigger, the small become smaller due to the energy within the system. And how they are actually used. This is the basis, basically. We have one tail or one section which is hydrophobic, does not like the water, and the other one is hydrophilic, which likes the water. Oil is oil and water, and that's basically the type of mechanism that they will absorb onto the oil. It could be ions, it could be surfactant, it could be particles, it could be polymer or protein. And once the oil is covered, you are forming a droplet, and this droplet then, once it's covered completely, it will not coalesce or aggregate with the other droplet, and this is the recipe of making one phase emulsion that it will be stable. Looking at gum arabic, what we see here, this is the fingerprint, and through the fingerprint we identify these fractions, which we call the arabinogalactan protein, arabinogalactan and glycoprotein, and this is the proposed structure. And we have also identified that this is actually the fraction responsible for the emulsification, because it has very little amount of protein. It's only 2%, but it is sufficient to coat the oily droplet, as you see there, and the carbohydrate, which basically the sugars, will stay in the oil phase, and this is how you make a nice emulsion using gum arabic. This is a good emulsion. The other one is a failed emulsion, and this is what you see. All the droplets are aggregating and going to the top. And this is a program, very quickly, the companies that have taken part in sending their material to us, and according to the system we developed, we advise them on the emulsion index and the parameters, and then they can choose this material to buy or the other. And this is the certificate we issue and classify this material according to the quality, and then the company or the user are free to use or to buy whatever product from the various suppliers. In addition to that, we work directly with the source, and here to train the Sudanese suppliers on how to undertake a sampling or statistical sampling method where they'll allow to actually sell a product. This material then is sent to a potential user, and then the user will have exactly the same material that they evaluated in their lab when they buy the actual quantity. Lastly, these hydrocolloid, they also have ability to interact with the protein, and this is really the nature of the food. It is not only hydrocolloid or protein only, but when they interact, they can form soluble or insoluble complexes, and this is what we use to control the texture. And the way to do it, we do what we call the phase diagram, and this will identify the ratio, the pH, and the desired condition where you can make these formulation. I think with this I will stop, and thank you all for listening.
Thank you very much. I think you have time for one question, please, if there's any questions. Neil?
Saphwan, maybe a bit of an unfair one. Is there any flexibility within the legislation that you know of that could allow a designer polysaccharide to be made via fermentation processes and still be called a polysaccharide?
I think as far as you can demonstrate that there's no chemical added and it is a natural product, you should be safe. But anything new within the food industry, it is extremely, extremely difficult.